I'm going to combine a couple of units here, units 2 and 3, combine the distributions. So this will be the same PowerPoint that you see in unit 3. But yeah, we'll spend some time, we'll have a whole lot of time on the quizzes and discussion. These are some terms. I'm not going to define them elsewhere, so I'll do them right here. A continuous distribution, this is for variable data or real numbers. Discrete distribution, this is one that is done with attributes or integers. Parameter is any kind of an analysis or of a population. And a population is everything we study, things of interest. And a statistic is when we take derive some kind of number or value based on a sample only. Okay, I'm going to start off with the central limit theorem. Sample means, and what you do is instead of taking the individuals and plotting those, you take a sample size, any size you want from a population, and you average it. You plot those averages. You plot the averages, not the individuals. And then to calculate the standard deviation, which is called the standard deviation of the mean, standard error of the mean, or sample standard deviation, they're all the same thing. You take the standard deviation and divide it by the square root of that sample size. You take the standard deviation and divide it by the square root of that sample size. This definition of the central limit theorem: samples of size n from a population. A lot of times you'll see from a normal population. It doesn't have to be normal, and as long as you take the outliers out, you can calculate the standard deviation for any kind of distribution. At least as far as I know, I've not seen one. The distribution of the sample means is normal. So in other words, we're making a normal curve no matter what the population distribution looks like, with the mean equal to the mean of the population. In other words, the average of the averages, if that makes sense. And the standard deviation, like we said, is the population standard deviation divided by the square root of the sample size. I'm not going to spend a whole lot of time on this slide. Descriptive statistics, two things you want to know about any data: the center point and how much it varies. The center point, or the central tendency, is mean, median, mode. The measures of dispersion, you got range or standard deviation. And what I want you to do is think about what happens when the data is skewed, and again relate that back to the central limit theorem and why we need the central limit theorem. We're going to talk a little bit about how to choose the right distribution. And what you want to do is what's called the probability density function. And what this is if you look at that picture on the right there, the area underneath that curve is equal to 100%, or 1.00. And this is for continuous data. If we're talking about attribute data, instead of doing the integration, we'd be doing summation. So in theory, if I was integrating from negative infinity to positive infinity, we'd add that little formula that would come up with would be equal to 1.00, or 100%. So what we're looking for is a cumulative distribution function. So in this case, we want to know what's the probability of getting some point between A and B. And if I knew that probability density function, all I would have to do is integrate that thing, plug in A and B, and calculate it. That's the cumulative distribution function. So how do I know that I got the right distribution? Well, I'm going to recommend you use graphical methods. Histograms are very good. Box plots, stem and leaf plots, or scatter diagrams. And I'll attach in the reading some information on that, what each one of those is. But basically the function for probability is there's a probability density function. We're not going to calculate that or try to determine that. We're just going to use that. But this is the underlying theory. Okay, so now we're ready to start doing some math. So first thing I do is define the problem. If you think you can get bigger or smaller, and only bigger or smaller, then you want to do a one-tail test. If you can go either way, then it's a two-tail test. We're going to talk a little bit about hypothesis testing and null hypothesis and alternative testing. And then we're going to do a test statistic. We're going to pick out the right one. We'll do the math here in a few minutes. calculate the p-value, the test statistic value, make an inference about the population, and then brag about it. Okay, in the Greenbelt course, we talked a little bit about hypothesis testing, and now we're going to expand on that a bit. In the Greenbelt course, we said the only one we worked with was the equal to. The null hypothesis basically says the group A is equal to the group B. They come from the same population. The alternate hypothesis would be they don't come from the same population. They're not equal. Also, we can do a one-tailed test. In this case, group A is less than group B. The alternative is group A is greater than group B. Or you could say group A is greater than or equal to B. The alternative is A is less than B. Now, interesting thing about null hypothesis, you can never be 100% sure of the null hypothesis. You cannot be 100%. And therefore, a null hypothesis can only be rejected or fail to be rejected. So you can reject it, yeah, it's not true, but you can't accept it. You can only fail to reject it. It cannot be accepted. Okay, and because you just don't have enough evidence. This is because you only got a sample, you don't know the whole population. So we got this null hypothesis. So we take a sample, right? And then we take the numbers from the sample and we crunch some kind of statistic from it, right, from the sampling data. And then we compare the number we get to a critical value. Most cases it's about 5%. And we're not going to do this by hand. We're going to use Excel. And then we look at that and we say, do we reject it or do we fail to reject the null hypothesis? And we'll get into this, like I said, next few slides. It's possible we'll make an error. If we got a 5% alpha, in other words, 5% chance we're going to make an error, and let's say the null hypothesis is actually true. A type 1 error says we reject that null hypothesis. That's the type 1 or an alpha type error. We reject the null hypothesis when it's in fact true, and that's possible. It is also possible that the null hypothesis isn't true, and we accept it, or did I say accept? Fail to reject. That's called a type 2 error or beta error. What we want is if the null hypothesis is true, we fail to reject the null hypothesis. If we think the null hypothesis is false, if its reality is false, we want to reject the null hypothesis. And we can set that alpha error, whatever we want, or the beta error. And generally it's 5%. If anybody's in the pharmaceutical, let me know, because that's 99%, or that's 1%. I'm not going to talk to this slide directly. If you want to know about descriptive statistics, take a look at that add-in video. I've got it in the readings. What I'd like to talk about is when we do the Excel calculations, whenever I put like equal norm dist, or equal to Poisson, equal binom, equal chi-test, whatever it is I put in there, it spits back some number like a 0.0002 or a 0.15. What that's telling me is that's the probability that the variation I'm seeing, whatever that is a result of random variation. So a 0.15 means there's a 15% chance that whatever I'm seeing is a result of random variation, and there really isn't a real difference. So I'm going to use this little saying: if P is low, H low must go. And that's how it relates to the hypothesis test. So I'm looking for about a 0.05 generally, or about a 5% probability that I can make a type 1 or an alpha type error. Those are odds I'm going to play with. I'm going to roll the dice on that. Again, if you're in pharmaceutical, it's 0.01 or 1%. But that's the relationship between Excel and this hypothesis testing. Excel will calculate the p-value, and then based on that, we're going to make the call on the calculation. And if the p is low, the null hypothesis goes. It's not random variation. There's something going on. Probability. I'm not going to spend much time on probability in the presentation. I expect to spend a lot of time in the discussion and also the quizzes and the readings. Some of the basic concepts. So one thing I want to point out here is all events have to add up to 100%. It can't be more than 100%, only 100%. Okay, simple events. These are their events that can't be broken down anymore, can't be decomposed. So if I roll on a dice, what's the probability of getting a 6? 1, 6. Compound event, that's the relationship between two or more events. So I've got 2 events, and let's say I'm going to say the dice example. What's the probability of rolling an even number? Well, that's 2, 4, 6. Those are my even numbers. What are my, let's say I have a probability of rolling something 3 or less. That's 1, 2, 3. Now, compound event would be, say, well, all right, what's the intersection of those? Well, 2 is the only one that's found in both those groups. What's the union of those things? Well, it'll be 1, 2, 3, 4, and 6, right? Those are compound. Event relationships. The complement is whatever it takes that's not in space that we're talking about to add up into 1. So if I'm talking about rainy days, happens 30% of the time, well, the complement of that would be days when it doesn't rain, or 0.7. Conditional probability, so I'm going to stick with the rain example. On cloudy days, 2/3 of the time it rains. So there's a condition. It has to be cloudy before it can rain. Mutually exclusive. One happens, but not the other is not possible. So if I were to reach in the drawer, I got 5 pairs of socks. 2 are black, 3 are blue. I reach in, I pull out a blue sock. I can't pull out a black sock at the same time. That's an exclusive. And then there are tests for that, right? And I'm not going to get into that. I covered a bit in the Greenbelt class. If you want to, we can go over it again, but there's no need for that. The 2 events are not mutually exclusive, and I'll have something in the quiz about that. The additive law says, well, it's the probability of the first plus the probability of the second. I'm going to subtract off the intersection of those 2 probabilities. And again, it'll be in the quiz. If you have a question, ask me. If they're mutually exclusive, it's just additive. So what's the probability of I've got 10 socks in a drawer. 2 are blue, 3 are black. What's the probability of pulling out a blue or black sock? Well, it's 0.2 plus 0.3 or 0.5%. Multiplicative law. This basically says if they're dependent, in other words, I'm playing blackjack. The odds of the, and I pull up 3 aces. What are the odds of pulling up another ace? Well, the probability changes, right? It went from 4 to 52 down to 1 in 49. That's a conditional multiplicative law. If they're dependent, I mean, that's a dependent law. If they're independent, they just multiply. What's the odds of getting a, say, blue and a black sock? Well, it's 0.2 times 0.3 or 0.6 of getting one of each. Again, quiz, discussion. Exponential, this is actually came out of Poisson. He knows that in reality, things like yeast growing in sugar water, it grows exponentially. And then when it dies exponentially too. A lot of things like this, radioactive decay, things like that. I'll give you an example in the readings or in discussion. The log normal. Back again, if you're talking about log, you can't have a negative number. So what the log normal does, it basically takes our random variable, does a transformation on it, and crams all the negatives between 0 and 1, and everything that random variable greater than 1 would be 1 or better, bigger on the on this table, and then you can analyze it. But that's what a log normal. If you ever need to use this one, I won't use it in this course. I don't like it. We got computers. But the logarithm of a random variable is normal. You can analyze it using this. Weibull just said, I'll just look at what we got and do a kind of a best fit curve on it, set some parameters on that curve, and then I can see what the probability is. That's a Weibull distribution. Okay, I put one of these into discussion, Unit 2 discussion. I can see this might be a live broadcast coming up on this. What I want you to do is, if you look at this, it kind of combines everything. It talks about the conditions, the different types of probabilities, and the different distributions actually are in here, embedded in here too. But if you look at the symbols, you should understand that, like P of A, all that stuff. It was in the reading. But what I want you to look at is like that first one in the upper right hand corner. What is the probability if you had 3 children? 2 would be girls, 3/8. See if you can get that answer. I can see this way. It might be a live video call sometime. Again, see if you can do the problems, and let's talk about the discussion. Okay, let's talk a bit about process capability. So we got the variation in the process. So what we're going to do then is compare it to what the spec limits are. And what you want is like a situation like on the left on this graph, where all the product seems to be within the spec limits. Even if it's not centered, if you got a tight enough process, you'll still be okay. Now, what you don't want is like the right-hand column, where you got too much variation in the process and it's outside the spec limits. That's just bad, even if it's centered. Or if you don't center it, you got that all that product that's outside the spec limit. So we can do a couple things. One is do nothing, right? Just, if you got the green situation, don't change it. Don't change it. Or you can change the spec. Let's say you got the upper right-hand corner. And everything works, right? So you make this widget. It's outside the spec, but it still works in the product. Probably your spec needs to be looked at real hard and change that, right? You can center the process. That'd be the lower left-hand or lower right-hand corner. Put that thing in the middle. Reduce variability. Again, upper right I'm looking at. Just tighten up that variability. Or just accept it. Accept the losses, right? A lot of times, like I said, if the specs are too tight, a guy makes it out of spec and it still works, you're in trouble because he doesn't know what the true spec is, so he's just going to try to guess at it. That's when you got issues. These are the formulas for process capability, CP, capability of the process. Upper spec minus lower spec divided by 6 sigma. CPK, that you're not going to be perfectly centered, so it's the minimum of the upper spec limit minus the average divided by 3 sigma. Or if you're close to the lower spec limit, the average minus lower spec limit divided by 3 sigma. I'll put some questions on the quiz. Make sure it get us to review this a bit. So I'm going to do a normality test. See if in fact I am actually a normal. And you can do this with any distribution. I'm just going to choose normal. First of all, and the reason I like normal is if you got a control chart, not a lot of out of control points, you're probably okay. However, if you're suspicious, you want to look at a normal curve. So the way we would do this is we would take a 1,000-piece sample, and we would expect 34.13% of that 1,000-piece to be within 0 and -1. 13.59% between -1 and -2, and 2.14 between -2 and -3, and 0.13 greater than 3. And we would sit there and we just say, okay, this is what we expect. This is our expected value. And of course, it works the same way in the positive because of the symmetry. So then I go back and I say, well, what did I actually find? Between 0 and -1, I expected 34%. How many did I actually count there? How many did I see between -1 and -2? How many did I see between -2 and -3? How many greater than -3? And then I look on the other side, 0, 1, 1, 2, 2, 3, and I look at these different bins. So I've got the observed, right? So before I had the expected, now I've got observed. This is the way the 1,000 pieces look. So I'm going to set up a quick hypothesis test. My null hypothesis, there's no difference between the observed and the specified data. So what I expected matched up pretty good with my observed, is what I'm saying. or then there's the alternate. There is no difference between the observed data and the specified distribution. So it didn't match very well. Well, whenever you hear observed versus expected, you naturally think of chi-squared, right? Yeah. All right, Scott. So what I would do is I'd count the number in between 0 and -1. That's my observed. And how many did I expect between 0 and -1? Subtract the difference, square it to get rid of that negative number. There's 1. Divided by the expected. And I do that for each one of those bins. Add them all up, and come up with some number, some calculated test statistic. And then I'm going to compare that to a critical value. You know, that was the chi-squared. There are other tests too. Kolmogorov, Smirnov goodness of fit test. And I'm not even going to talk about how they do that. Anderson Darling modified that test a bit. Non-normal distributions. This is where that log normal comes in. What you do is you take the logarithm and see if that makes a normal curve, and then you can do the goodness of fit test. But I've been doing this for 25 years, and I've never had to do one of these tests. If you come up with that where you have to do it, let me know. We'll work on it together. It's not that hard, really. It's just plug and chug. But usually, if I find if it doesn't follow a specific distribution, because my data's wrong, there's something wrong with my data, got outliers or something. Now, if you got to worry about probability for non-normal data or for attribute data, this is how you do it. For non-normal data, just transfer the data again to a normal curve. I'm not even going to discuss it here. For attribute data, you look at your control charts for attribute data, or otherwise you take a lot of data and use proportions. Are your proportions good enough? And I'm going to tell you right now that in today's world, if you find one out of spec, you're not in control. You don't have capability. Okay, last slide. Performance metrics that are got a Six Sigma tone to them. Defects per unit. What this is if you got less than a perfect process, a lot of times a product or service will have more than one defect. For example, my car it's got like a cracked windshield, the door handle's broken, sometimes the heater doesn't work. So it's one car, but I got 3 defects, right? Defects per opportunity, sometimes that's written defects per million opportunities is another way of looking at that. What they do is they say, well, how can I vary products of various complexity or medical care of various complexity? How can I compare the two? Well, what you do is you look at how many ways they can screw it up. So if one's got 5 opportunities to make a mistake, well, that's 5 opportunities, defects per 5 opportunities. Another one might be more complex, might have 100 ways to screw it up. So you see, then what you do is by making defects per opportunity, you can kind of level it, compare apples to apples. Yield, this is just another name for first pass yield. There's a relationship between first pass yield and defects per units. It's based on Poisson's distribution. First pass yield is equal to exponent to the negative DPU, or DPU is equal to the negative natural log of first pass yield. There'll be some examples in the quiz. Rolled throughput yield. A lot of times first pass yield is just what you lose on the final step. Rolled throughput yield said, okay, got 100% going into the start of a process. How many actually make it through? And again, there'll be some examples on the quiz. Sigma level, I'm going to address that in discussions, but basically it's just a way of measuring how good a company is based on its PPM.